Welcome to odd-even sort, also called brick sort. This algorithm alternates between two phases in each iteration. The odd phase compares adjacent pairs at odd positions, 1, 2, 3, 4, and so on. The even phase compares adjacent pairs at even positions, 0, 1, 2, 3, and so on. Because comparisons within each phase are independent, this algorithm is naturally parallel. It repeats until a full iteration passes with no swaps. Let's watch it in action. Pass 1, odd phase. Comparing 39 and 1. 39 is greater than 1, so we swap. Swapped elements at positions 1 and 2. Comparing 15 and 99. 15 is not greater, no swap needed. Pass 1, even phase. Comparing 80 and 1. 80 is greater than 1, so we swap. Swapped elements at positions 0 and 1. Comparing 39 and 15. 39 is greater than 15, so we swap. Swapped elements at positions 2 and 3. Pass 2, odd phase. Comparing 80 and 15. 80 is greater than 15, so we swap. Swapped elements at positions 1 and 2. Comparing 39 and 99. 39 is not greater, no swap needed. Pass 2, even phase. Comparing 1 and 15. 1 is not greater, no swap needed. Comparing 80 and 39. 80 is greater than 39, so we swap. Swapped elements at positions 2 and 3. Pass 3, odd phase. Comparing 15 and 39. 15 is not greater, no swap needed. Comparing 80 and 99. 80 is not greater, no swap needed. Pass 3, even phase. Comparing 1 and 15. 1 is not greater, no swap needed. Comparing 39 and 80. 39 is not greater, no swap needed. 5 elements are now sorted. Congratulations! You have successfully completed the odd-even sort lesson. Let's review what happened. The algorithm sorted the array in 3 passes. It made 12 comparisons each time it checked an adjacent pair during the odd or even phase. It performed 5 swaps each time a pair was out of order during a phase. The original array was 80, 39, 1, 15, 99. After sorting, the array became 1, 15, 39, 80, 99. Here are the key takeaways from this lesson. First, odd-even sort alternates an odd phase comparing pairs at odd indices and an even phase comparing pairs at even indices, swapping out of order pairs in each. Second, elements propagate toward their correct positions across alternating phases. Both ends of the sorted region grow over successive iterations. Third, in the worst case, the time complexity is order n squared. This happens when the array is sorted in reverse order. Fourth, the space complexity is order 1. It sorts entirely in place using only a few temporary variables, requiring no extra memory. Interesting insight, 5 swaps out of a maximum of 10 a typical average case run. Now let's explore the time and space complexity of odd-even sort in detail. Best case O, n. On a sorted array, the first odd phase finds no swaps and the first even phase finds no swaps. The algorithm exits immediately. Average case order n squared. For a random array, alternating phases propagate elements similarly to bubble sort, requiring approximately n squared over 4 comparisons. Worst case order n squared. On a reverse sorted array, elements must bubble across many alternating phases, resulting in order n squared total iterations. Space complexity order 1. Odd-even sort is an in-place sorting algorithm. It only needs a few temporary variables regardless of the input size. No auxiliary arrays are created. When should you use odd-even sort? Odd-even sort shines on parallel hardware where all comparisons within a phase can execute simultaneously. It is also used in sorting networks and hardware-level implementations. When should you avoid odd-even sort? Avoid odd-even sort on sequential hardware where you gain no benefit from its phase independence. For large inputs, prefer faster algorithms like merge sort or quick sort. That's everything about odd-even sort. Well done on completing this lesson.